Welcome all. In this video, we will learn about code optimizations in compilers. Code optimization is a collection of techniques to produce a better object program than the most obvious one for a given source program. Let us try to understand this statement. The input to the compiler is the source program, which is a specification of some computation. And as output, the compiler produces the object program, which is again a specification of the same computation but in a different form. For a given source program, you could have multiple object programs, and the compiler aims at producing the best object program for the given input. So this takes you to the question, when do you say an object program is good? Or equivalently, you could ask, how will you determine the quality of an object program? Generally, we rely on two parameters to measure the object program's quality. One is the execution time and the other one is the space or the memory requirements. Obviously, we want the object code to take less time for execution and also to take less space in memory. You could make your object code run faster or take less space, or even both, through the use of program transformations, what we call as optimizations. And the compilers that perform this optimization are known as optimizing compilers. Now this term optimization is some sort of a misnomer because there is no guarantee that optimization will always result in the best object code. A better term would be code improvement, but traditionally the term optimization is used in the literature, and in this video also we will be following the convention. Moving on, there are two categories of optimizations. The first category, known as machine independent optimization, the compiler improves the target code without considering any properties of the target machine. It takes the code, identifies the places where it can optimize, and then it performs the optimization. For example, it may identify that certain variables are introduced unnecessarily just to hold values of constants. So what the compiler can do is it can just replace the variables with the corresponding constant values. This is somewhat different from the second category, which is known as machine dependent optimization. So here the compiler also takes into consideration the properties of the target machine. So it could consider properties like how many registers are available and availability of certain special machine instructions. So let me give an example. You might recall that left shifting a number once is equivalent to multiplication of the number with 2. Similarly, right shifting once is equivalent to division by 2. So if the compiler sees an instruction to multiply a number with 2 or powers of 2, what it can probably do is it can replace that instruction with a sequence of left shift operations. Similarly, the instruction to divide a number by 2 or divide by powers of 2 can be replaced with a sequence of right shift operations. Now this is indeed an optimization because the shift operations are generally cheaper when you compare with the multiplication or division operations. Now you could ask, okay, what is the purpose of doing this optimization, or why should you bother about optimization? Let us see why. So you know that this optimization phase sits between the intermediate code generation phase and the target code generation phase. It happens that the intermediate code generation phase could introduce some inefficiencies in the code. For example, it may introduce unnecessarily certain copies of variables, or it may compute the same calculation multiple times. So all these may not be deliberate, but it happens at times. The optimizations could remove all such inefficiencies. Not only that, the optimization can also do more. So we have already seen an example where an expensive operation is replaced by a cheaper operation. Another example is suppose you want to add 1 to a number, or you want to subtract 1 from a number. Instead of doing addition or subtraction operations, what you can probably do is the compiler can go for auto increment or auto decrement operations, which are again cheaper with their addition or subtraction counterparts. So before diving into the further details of optimization, we will see two definitions which are very important and very useful for our upcoming discussions. The first one is the basic block. So basic block is a sequence of consecutive statements that are entered only at the beginning, and once entered, the statements are executed in sequence without any halt or branching except possibly at the end. So let us take an example and see what the statement says. So this code one shown here is an example for a basic block. So you have 6 statements T1 to T6. So the flow of control can enter at this particular point. And once the flow starts from this point, all the statements T1 to T6 are executed without any stop or without any branching. And finally, when the last statement T6 is executed, the control gets out of this. So this is indeed a basic block. Now on the other hand, this code 2 is not a basic block, because the first statement itself has a go to instruction, which is a branching instruction. So this code is not an example for a basic block. The second definition that we will see is that of a flow graph or control flow graph. Generally we use the short form CFG. So this CFG is a directed graph that is used to portray the basic blocks and the flow of control between the basic blocks. So a graph means it should have vertices or nodes and edges. So with the CFG, the nodes correspond to the basic blocks. Okay, the nodes of the flow graph are the basic blocks. Now coming to edges, when will you add an edge between two nodes? There's a directed edge from the block B1 to block B2. Remember, the nodes correspond to basic blocks. So there is a directed edge from the block B1 to block B2 if and only if B2 could immediately follow B1 during execution. So this happens in two cases. Either there is a conditional or unconditional jump from the last statement of B1 to the first statement of B2. So that means in the basic block B1, in the last statement, there is a conditional or unconditional jump instruction that takes you to the first statement of B2. So this is one possible case. Now the second case, what it says is B2 immediately follows B1 in the original order of program instructions, and B1 does not end in an unconditional jump. So what this says is the first statement of B2 follows the last statement of B1 in the original order of the code, and also the last statement of B1 has no jump instruction. The last statement is not a jump instruction. In that case also we say B2 immediately follows B1. So in these two cases, we add an edge from the block B1 to the block B2. So if you have an edge from B1 to B2, what you say is B1 is a predecessor of B2, or equivalently B2 is a successor of B1. So let us take an example. This figure 1 shows a flow graph. You have three blocks, B1, B2 and B3. Now coming to the edges. The last statement of B1 is followed by the first statement of B2. So you need to add an edge from B1 to B2. Similarly, you can justify this edge because the first statement of B3 follows the last statement of B2. Now you will also find that the last statement of B2 is actually testing a condition. Okay, so the condition is true, it takes you to the first statement of B2. So there should be a self loop, there should be a loop from B2 to B2. In a similar way, you can also justify the presence of this loop, self loop from B3 to B3. So we will stop for now. In the upcoming video, we will learn about principal sources of optimization. Typically, we will discuss about the function preserving transformations and its examples like common subexpression elimination, copy propagation, constant folding, etc. Thank you.